Okay, welcome to the second day of the Mandelstam workshop. So pleased to have the first talk this morning, Blaise Gouteraux on density waves, bad metals, and black holes.
Thank you for the introduction and for the invitation to give a talk at the workshop. I'm very glad that I'm visiting here. So in this talk, I want to tell you a little bit about what's a natural continuation of what we discussed during the lectures. During the lectures, we talked about hydrodynamics and momentum relaxing metallic fluids. I also told you a little bit how we could compute this momentum relaxation rate to model this kind of system using gauge gravity duality. So what I want to talk about in the seminar is what happens when you don't simply break translations explicitly, but when you break them spontaneously. So when you break them spontaneously, you have a condensate that forms and you have some periodicity that appears. And this can go either under the form of some charge density wave or some electronic crystal. And so this is the kind of systems that I want to study using both tools that we saw during the school, both hydrodynamics and gauge gravity duality. More specifically, the goal of the talk is I want to discuss the potential relevance of pseudo-spontaneous symmetry breaking, specifically of translations to transport across the phase diagram of cuprate ITC superconductors. For that, I want to look at hydrodynamic transport in the presence of pseudo-gallstones, and I will explain to you how this leads to so-called bad metallic behavior. I'll make clear what this means. And then I want to present some effective holographic time model of transport, which we'll use to compute the resistivity for charge density wave states. These are the references that this talk is based on. So it's based on a few papers that have been appearing since last year. So these two are hydrodynamic papers together with people that are in Stanford, Luca de la Creta, who's Sean Harkin's student, and Anna Kalshan, who used to be a postdoc there and now has moved to IAS. And these two more recent ones, they're holographic papers, together with Andrea Moretti, who's a postdoc in Brussels, Daniela Reyan, who's in Porto, and Daniele Musso, who's in Santiago de Compostela. Okay, so what's the motivation? The motivation is to try to understand what's going on in these two plots. So the left-hand plot is a plot of the resistivity, the DC resistivity as a function of temperature. And what happens in many so-called bad metals, so these are specific compounds, but I won't really tell you exactly what they are. Let's just say that they exist. And what happens in these compounds is when you measure the resistivity, you find two things. First, you find that it's linear in temperature across many decades or even hundreds of kelvins. So that's the first problem, because for a conventional weakly coupled metal, Landau-Fermi liquid theory tells you that the resistivity should go like T squared. So the fact that the resistivity goes linear in T is already presenting a challenge, because there's no consensus on the mechanism that produces this linear in T dependence. There's a second problem, which is that the resistivity grows without bound. There's this so-called Moth-Joffe regular bound that applies to essentially all weakly coupled metals, and which is just a reformulation of the fact that since the elementary objects that are describing the low energy dynamics are quasi-particles, in order to even talk about quasi-particles, these objects should have a quantum wavelength, which is smaller than the mean free path. Otherwise, you cannot describe them as coherent states. So this is related to some basically Heisenberg uncertainty principle between the quantum wavelength and the mean free path. So when you impose this inequality, you transcribe this in the computation of the resistivity, you find that the resistivity should be bounded from above by a certain value that depends, say, on the lattice spacing. It's not a very precise value, but at least it gives you some order of magnitude. And as you can see from this schematic, essentially for all these bad metals, and there are many of them, we've discovered many of them, the resistivity just crosses this bound. So the crossing of the bound tells you that the quasi-particles cannot be responsible for transport in these systems. So you have to think of something else. This is a sign that these systems are strongly coupled, essentially. So that's one puzzle that has to do with DC transport. Now you can look at what happens when you turn on frequency dependence. So you measure the real part of the frequency-dependent conductivity, you turn on some oscillatory electric field, and you measure the response. And this is the response coefficient. This is what it looks like. This is at low temperatures, the blue curve, and now going down, you're increasing temperature. So the red curve is room temperature, let's say. So you see that there are two things that are happening. So at relatively low temperatures, you have these peaks into that zero frequency. So this is very much like what we saw in the case of a metal where momentum relaxes slowly. You remember that we had this sharp Judo peak that was centered at omega equals 0. So this looks like that, except that here the width of the peak is of order the temperature. You remember I was telling you that in order for this slow momentum relaxation picture to apply, you needed the width of the peak to be orders of magnitude smaller than temperature, and here this is already not the case, even though this is a peak centered at omega equals 0. Then even worse, when you increase the temperature, you see that the peak is getting squashed and broadens out. It eventually even moves off to non-zero frequencies. Now, you might be thinking that, all right, this is some UV resonance that's kicking in and it's giving me this peak. But actually, when you look at the frequency scales, these are extremely far infrared peaks. They're very, so like DUV in these systems would be order electron volts. These peaks, you measure them order maybe a few tens of milli electron volts. So they're really in the far infrared range, and they should really be part of the, the effective IR dynamics that describes these systems. All right, so these are the two challenges that at least I would like to understand better.
But it seems that the resistivity grows slower than for normal metals, right?
So what would happen is that for a normal metal, you'd have this T squared and then it would saturate.
Okay. So I'm just wondering about the bad thing. Are they really worse conductors?
So
metals,
what bad metal means is that when the resistivity crosses this bound, so the conductivity is becoming very small.
So
this is why they're called bad metals.
Okay.
Because a good metal it's one of these metals where the conductivity, so the resistivity is bounded from above. So it means that for a good metal, the conductivity is bounded from below. So in a sense, this is some definition of a good metal. It's a metal that has a conductivity which is above the MIR bound.
At room temperature?
At, say, room temperature. Yeah, I could have drawn, for a conventional metal, you can see that the resistivity saturates below the bound. Okay, so there's one natural interpretation of this linearity resistivity, which may or may not be the correct one, but here goes. So you might still insist on trying to interpret this linearity dependence in terms of some transport timescale. So then what would you do? You do the simplest thing you could think of. You would write a formula that's similar to the formula we saw in the first two lectures for a metal with a slow momentum relaxation. So this is like some Judo type formula where you have the mass of the charge carrier, the density of the charge carrier, the unit charge, and the transport timescale. And then you would equate that to temperature, because that's what you see in the experiments, and from that you could extract the transport timescale, and you would find that essentially this goes like h power over kBt. Now this is a very interesting timescale. Essentially, people believe that, well, first it's a timescale that you can define in any system as long as you have finite temperature, just by dimensional analysis. You take temperature, you ask yourself, what fundamental constants do I have? How do I make a timescale out of that? And naturally, you'd be led to using the Boltzmann constant, the Planck constant, you put that together, and you would form something of order h power over kBt. Now this is a timescale that appears all over the place in, say, quantum criticality. At a quantum critical point, you essentially have a scale invariant description, you have a CFT, and then temperature is the only scale that you can use in order to make up for the scaling dimensions of any observables. So this would be the natural timescale in any quantum critical system. It turns out that in many of these bad metals, we believe that there are quantum critical points around, so it somehow connects to this picture. It's also expected to be the fastest equilibration time that nature and quantum mechanics allow. Essentially, again, by some uncertainty, Heisenberg uncertainty principle arguments. And indeed, when you plug in numbers, at room temperature, this timescale would be 25 femtoseconds. That's an extremely short timescale in terms of experimental timescales. So somehow this linearity resistivity is suggestive of this Planckian dynamics. What about the frequency-dependent conductivity? So one exercise we did is so you remember, this is schematically what the experiments look like. Here I'm just depicting some theoretical impression of what the data really look like, but if you look at the data, this is kind of the picture you see. So then what you can do is you can catalog the position of these peaks and the width of the off-frequency axis peaks. So you catalog them, and then you plot them versus h bar over kBt. Right, so this is what I'm doing here. I have the position of the peak, and I have the width of the peak, and I'm plotting them here and there versus temperature, and I'm spreading them using the DC conductivity. So this MIR bound would be somewhere here, roughly speaking. So all of these materials, you can look them up in the paper if you're interested, but let me not discuss them in any detail. There are high TC superconductors, but there are other types of bad metals as well. So all of these materials are really bad metals because they all have DC conductivities that are below this Martioff-Regel bound. This is a log-log plot, so you can see that there's some dispersion of the points, but still there's a general trend that the position of the peak and the width of the peak seem to be controlled by the same Planck timescale as the DC transport. So the lesson here is that these Planck dynamics, they show up not only in the zero frequency data in the resistivity, they also show up in the frequency dependent conductivity.
So did you say that these bad metals are also high TC superconductors?
Including high TC, yes.
Or?
Yes. So high TC superconductors at low enough temperatures become good metals because their resistivity would be below this bound, but at room temperature they're typically bad metals. So these are all room temperature peaks essentially.
Yeah.
So, right, these two observations about DC and AC transport suggest that these Planck dynamics are really some defining feature of transport in these materials. But I won't, this would be a whole other talk, but there's been a lot of discussion over the years about Planck dynamics at black hole horizons, especially in the context of maximally chaotic systems, etc., etc. So let me not cover this whole field, but I'm sure that at least you will have heard of this kind of literature, that black holes are fast scramblers, etc., etc. So people believe that the horizons of black holes are also governed by the same Planck dynamics.
That the diffusion bound related to that?
Yeah, so I don't exactly. So this is what I'm thinking of, and I specifically don't want to enter into that because yes,
expression looked exactly the same. So
yes. So I don't want to talk about that because it would take too much time. But essentially, this is what I have in mind. So what it suggests is that there's some sort of universal low energy effective theory that would describe both of these systems. So to put it a little bit more pictorially, so we have these two very different systems. Here's a black hole in ADS. There's some crystal of a high TC superconductor, and they're very different on macroscopic scales, so we shouldn't try matching the UV theories. At least from my point of view, I don't think this is necessarily the best thing to do. But certainly it seems that the IR effective description at low energies, it shares a number of features. So it gives you some hope that you can understand something about one system by studying the other system at long wavelengths. Very much in some RG flow spirit. Okay, so let's go back to our bad metals. We'll talk about black holes a little bit later in the talk. And what I want to do, I want to explain to you how you can use hydrodynamics and combine that with spontaneous translation symmetry breaking. And what we'll see is that it naturally leads to small DC conductivities, so bad metallic behavior, and I will explain to you what I mean by small in this context. And it explains, at least it gives a mechanism. It might not be the right one, but it certainly gives a mechanism by which you can see a peak moving off axis in the frequency-dependent conductivity. And also we'll play a game at some point where we see that we can naturally relate the timescale that governs the DC resistivity and the location of this peak. And it won't explain why that timescale is the Planckian timescale, but it will explain, it will give again some mechanism by which these two timescales can be understood to be the same. Okay, so that's what we'll do. Any questions so far before I start on hydrodynamics?
When you try to relate like this quantum behavior of this black hole and the CFT behavior, field theory thing. Is the h gut literally the same? Meaning the h gut in the CFT would be just the usual.
The what?
The Planck's constant h bar that you're
Yes.
saying. I thought that when you do ADS CFT, the h bar of gravity is like 1 over n, right? Is that not the case? Or am I confusing something?
I would say that each bar is just each bar. No.
I thought that the quantum corrections in gravity are controlled by 1 over n corrections, right?
Sure.
So when you said that there's a quantum mechanical, like this is an inherently
Sure,
quantum
but
mechanical.
for instance, so you're right,
Yes.
but on the other hand, take the entropy.
Right.
In principle, there's an h bar there, but this can be described by a purely classical configuration. Right, and take the Hawking temperature, there's also an h bar, and the point is that you can still describe the system as some classical macroscopic system, because when you multiply the two in the first law, the h bars cancel out. So even though you're using a classical description, there's still something intrinsically quantum about it.
So quantum or classical gravity side and the field theory side are different.
Yeah, that's what I was confused about, because it looks like he's having the same expression, the same h cut on both the sides. So I was thinking that, I don't know, maybe it's a very nice question, sorry.
I think it's okay, like, as long as you, like, for instance, for the Hawking temperature, you put an h bar there, and
For example, you question Laplace constant and chaos bar in both the field theory and the gravity. So there is h bar.
Yeah,
both
this
sides.
h bar on both
But
sides.
also in gravity you also have n and
Right.
h bar.
Right. Yeah, okay. Very nice question,
Definitely
sorry. So
move on.
maybe.
okay, so why do I want to start talking about spontaneous symmetry breaking? So this is a schematic depiction of the phase diagram of high DC superconductors. And so this is temperature on the vertical axis and doping on the horizontal axis. Doping is just telling you something about the atomic composition of the material. Essentially, it's a measure of how many charge carriers are available. So at zero doping, there are no conduction electrons, so you have some anti-ferromagnetic insulator, nothing moving. Then you start doping it, and the material starts to conduct. But what happens is that there's this superconducting instability that you hit very quickly for mid-doping values. And it's called high DC superconductivity because the maximum critical temperature is usually way above what can be explained by the BCS theory of superconductivity. Now, above there's this strange metallic phase, which is essentially where all these measurements that I was mentioning are made. This is where the resistivity is linear in T, so it doesn't behave like a conventional Fermi liquid, which is more like this part of the phase diagram. But then here, at underdoping, so this is optimally doped because this is where TC is highest, and when people talk about underdoping, you're between zero doping and the optimal doping. And here people have detected lots of charge ordering phenomena, or at least periodicity. So it could be spin density wave, it could be charge density waves. So here there's a lot of spontaneous translation symmetry breaking. They've even detected them, there are recent measurements that have detected them here. So it's kind of natural to think that if you have charge order here and some version of charge order there, then you could have fluctuated, some kind of fluctuating charge order also in this strange metallic region. So this is the logic of why we thought that it could be interesting to try to see what hydrodynamics has to say about charge density wave transport. Okay, so let's do that. As I told you, the fact that the resistivity is linear in T suggests that the quasi-particle is short-lived because they would naturally have the lifetime would naturally be of order of this Planckian timescale, so that's a very short timescale. And so these are not the right objects to describe late time transport. So one thing that one can do, it's certainly not the only one, but one thing that you can do if you just care about long wavelengths, then you can try to understand these systems using hydrodynamics. So if you just have a fluid, so no specific spontaneous symmetry breaking, then you would just have energy conservation, momentum conservation, and charge conservation. But what we want to have is a charge density wave. So when you have a charge density wave, you break spontaneously translations. Here I'm depicting a crystal, but it won't really matter for the purposes of this talk, whether I'm breaking translations in both directions or just in one. So this is a crystal, so it's in two directions. So what we want to do is describe a charge density wave. So it means that the charge density looks like that. There's some periodicity, and there's some amplitude. So here I will imagine that this is equivalent of the condensate for a superconductor, for instance. So this I will imagine that I'm in the region of the parameter of the phase diagram where the charge density wave has condensed. So this part, the amplitude is not fluctuating. However, what will fluctuate when you're in the condense phase, is the phase of this wave. And the phase of this wave is precisely the phonon of this electronic crystal. So here I don't mean that this picture is not meant to depict the atomic lattice. Here what I'm saying is that there's this strongly coupled electronic fluid that undergoes spontaneous spatial ordering. So this is the electronic fluid. This phonon is a phonon of the electrons, not of the atoms.
So X is just one-dimensional.
Yeah. I mean, you could do this with X and Y and whatever you mentioned, but here for simplicity, I will just write everything in 1D. But it doesn't really matter. The formulae will be the same. So now what we want to do, you saw that I had conservation equations for densities, energy, momentum, and charge densities. And now I need to write an equation that tells me the dynamics of this Goldstone node, because the Goldstone couples to everything else. And the way you do that is by just realizing that since this is a Goldstone of spontaneously broken translation symmetry, what it means is that this is canonically conjugate to momentum density. Because translation symmetry means conservation of momentum. So if I break that spontaneously, I get a Goldstone. And by definition, this Goldstone has some canonical commutation relation with momentum. So this is schematically what it looks like. This is a Kronecker data. Then I can write what psi dot is. Psi dot is just the commutator of the Hamiltonian with psi. And here, I mean, sure, if I knew the microscopic Hamiltonian, I could plug that in, but here I'm doing effective theory. So I don't need the microscopic Hamiltonian. I just need the effective Hamiltonian. The effective Hamiltonian will always contain a term that's just momentum times velocity. So in relativistic language, this would be like u mu t mu nu. Now, if I plug this in the commutator, now you see that I can pull out the integral, then I can use this relation to simplify this part, and then I would get the integral of v times the delta, integrate that, and this would give me v. So the equation that governs the dynamics of the Goldstone is psi dot equals v, where v is just the velocity. This is exactly the same kind of relation. This is why I'm calling it a Josephson relation, as you would get for the superfluid phase in superfluid hydrodynamics. Except that now, for a superfluid, the psi would be the superfluid phase, and instead of v, I would get the chemical potential, because the superfluid is the spontaneous breaking of u1. So the charge density would play the role of momentum, and the chemical potential would play the role of v. So this is the same logic.
You said that here charge has non-zero expectation value.
Yes.
What?
I could add a constant that I haven't added.
But doesn't it also lead to spontaneous breaking of the u1 of which this charge was a conserved quantity?
No, I don't think so.
It doesn't.
No, the charge just has, so there's some background value,
Okay.
and then there's some modulation on top of that. This doesn't break the U1 spontaneously.
Well, actually, that's a simple question. Why you just don't start from putting this cosine qx plus vt?
Where?
In just beginning.
You mean in these equations?
No. Next one. Here, write down this AC charge density wave.
Here?
No, row x. Second row.
Here?
No. The top equation.
Yes.
The introduction of
You
Goldstone modes.
introduce this psi, but if you look at the equation, psi is like vt, and you can start from kx plus vt.
Sure.
Well, what's the
Yes.
point of discussing this? I don't know.
Of doing it this way?
Yeah.
Well, whatever you prefer. I agree. I agree, you could also see it this way. I agree. These are two different ways of seeing it that give the same result. It's just that depending on your taste, you might like. This discussion makes it clearer in terms of, symmetry, generators, etc. But yes, I'm not claiming that this is the only way of getting to that equation.
But
Yes.
there is a lot of difference in physics. So psi is supposed to be the fluctuation, which is a phonon.
Yes.
So it has a dispersion, a spectrum, and so on.
Yes, yes. And that would
Why-
come out from hydrodynamics.
Why just writing it as Vt would just be nothing here.
No, but this would be your equilibrium state.
That's right. That would be the
Yes. And then you would perturb around that, and the fluctuations.
So this is a fluctuation.
Yes.
Yeah. Okay.
I could rewrite this whole thing as a psi and then decompose it as some background value plus some fluctuation.
Background would be
Yes.
Vt.
Okay, so now what we need to do is the same thing that we did during the lectures. We need to give constitutive relations to currents. I won't tell you the whole story because I don't need it, so I'll just tell you the ingredients that I need. I just need to look at the electrical current because I just want to compute the conductivity, and I'm turning off here a bunch of terms that don't matter in order to compute the conductivity. The only two terms that I care about is the zeroth order in derivative term, that's still rho times V as usual, and then the term that's first order in gradient of the chemical potential with a coefficient that I call sigma naught. And as I explained, this is a diffusive transport coefficient that tells you that charge can be transported without momentum drag. So I can imagine killing this term and I would still have a current just by having a gradient of chemical potential. Now to understand a little bit better what this is, I could imagine being at zero density, so this would be slightly different. Then I would have particle pair creation in a CFT. What would happen then? I would create a particle and a hole. They would go in opposite directions. So the total momentum would be zero, but because they have opposite charge, their currents would flow in the same direction. And I would get a non-zero conductivity, and this conductivity would precisely be this guy. So this is a guy that tells you about charge transport without momentum drag, except that now I'm also saying that this applies at non-zero density, not just at zero density. Okay, so one more thing that we need to understand is that if you have a charge density wave and you don't break translations explicitly, so if your sample is completely clean, then the conductivity will be infinite. For the same reasons as we discussed during the lectures, because I haven't broken translations explicitly, I've only broken them spontaneously, so there's no way for momentum to relax, so the conductivity will be infinite. So what we need to do is we need to add a small amount of, say, disorder, so that momentum will relax. Except that now several things happen. So for a metallic fluid, the only thing that happened was that you would just turn on some effective term that relaxes momentum in the momentum relaxation equation. But here now we have a Goldstone. This Goldstone is the Goldstone of spontaneously broken translations. Except that now what I'm saying is I'm also, on top of that, weakly breaking explicitly the same symmetry. So what this does, just from field theory arguments, is that it's going to give a small mass to this Goldstone. As long as the explicit breaking is weak, the Goldstone will just acquire a small mass. If that mass is small enough, then the Goldstone is light enough that you need to keep it in the long wavelength dynamics. If you break the symmetry strongly, then the mass becomes big, the Goldstone freezes, and then it would decouple from the low energy dynamics. But here I'm imagining that I'm only breaking the symmetry weakly. And typically what would happen is that the charge density wave would get pinned by this breaking of, explicit breaking of disorder. So typically when you apply an electric field, there's some threshold electric field before the charge density wave starts moving, because otherwise it gets pinned. To understand a little bit better, we can look at what the formulae are. So I've tried to put both the weakly disordered metal case and the weakly pinned CDW case, so that you can contrast with what I was telling you the last few days. So you remember that for a weakly coupled metal, this is what the conductivity would look like. Importantly, there would be this pole purely imaginary with a lifetime that's given by the momentum relaxation rate. And when you took the DC limit, the DC conductivity would be 1 over the momentum relaxation rate. So if this is a small parameter, then the DC conductivity would be big. So this would be a good conductor. So this is what this picture shows. And then the blue curve, orange curve, and green curve are what you get when you increase the value of this guy. Now, on the other side, this is the formula that you get for the optical conductivity of a charge density wave. You see that it looks a little bit different, because essentially now you have this pinning parameter, omega naught, that appears in the denominator. And this has shifted the location of the pole. Instead of having a purely imaginary pole, and now the pole has a real part because of this guy. And because the pole has a real part, it shows up as a peak at finite frequency, not at zero frequency. Now the fact that there's a non-zero DC conductivity is related to the fact that this guy is non-zero. This you see right away, right? Because if I set omega to 0, then this whole term drops out. It's completely killed. So now the DC conductivity is given by this sigma naught, by this incoherent diffusive transport coefficient. So it's telling you that what controls the DC conductivity in these two systems is very different. For the weakly coupled metal, what controls the DC conductivity is momentum relaxation. So if that is slow, then the DC conductivity is huge. Whereas for the charge density wave, the fact that you have this Goldstone and that the Goldstone has a small mass sort of short circuits the dynamics of momentum relaxation. So now the DC conductivity is controlled by completely different processes, by these incoherent diffusive processes. It has nothing anymore to do with momentum relaxation. So in particular, what this means is that if you want to compute, so you remember that in the lectures, we computed the DC conductivity essentially by computing this momentum relaxation rate. But if you're in a charge density wave state and you want to compute the DC conductivity, then you need to compute a different object. You should compute this sigma naught. And since momentum relaxing effects only come at subling order, you can just compute that in the clean theory, in the theory where you don't have any impurities. I'm stressing this because essentially that's what we'll do using AVA-CFT in the second half of the talk. Any questions? This is one of the important slides of the talk, to really understand that there's a strong difference between transport in a weakly momentum relaxing metal and in a weakly pinned charge density wave. That it's completely different processes that control the DC conductivity, and that the frequency dependent conductivity looks very different. Here, different. Yes.
How many zero was the Goldstone?
So here the effects of the Goldstone are hidden in there. This is the mass of the Goldstone essentially, up to some other parameters that's not very important.
So the physical difference between the two pictures is spontaneous.
Yes, exactly. And you see that if I turn off this mass, so if I kill the Goldstone, then these omegas simplify out, and I will recover the same formula as before. And if I increase the mass, then the peak is shifting to the right. So the higher pinning, so this omega naught really gives you the location of the peak. So the larger it is, or the peak is shifted to the right. Okay, I'm going to add another ingredient to the mix. So, in 2 dimensions, you may know about BKT phase transitions in superconductors. You have vortices that form, and at some point these vortices, the topological defects, where the superfluid phase is not defined because the order parameter vanishes at the vortex. And at some point they stop moving. And when they move, since the order parameter vanishes there, it means that inside the vortex you just have a normal fluid. This normal fluid is dissipative, so when these vortices stop moving, they start contributing to the resistivity. So this eventually destroys the superconducting phase when these vortices proliferate. This is the BKT phase transition. The same applies to crystals or to charge density waves in 2 dimensions. Except that now the topological defects are no longer vortices, they're called dislocations. So this is the picture for a crystal, and you see that it's a hexagonal crystal. So each atom has 6 neighbors, except for this guy. This guy has 5. This is what a dislocation is called. And if you increase temperature, or if you increase the magnetic field, then these defects can start moving, and they will again destroy the ordering, the spontaneous symmetry break. At some point, you will just restore the symmetry that you had spontaneously broken. In 1D, this is a picture in 1D. This is what it looks like. So you have these lines of constant phase. So there's a phase gradient in this direction. And at some point, you see that I'm skipping a line. So the phase winds around that and gets relaxed when this starts to move. So essentially, the way that you model the effects of these moving topological defects is by giving a relaxation rate to the phase, to this Goldstone node that we have in the system. You remember that the equation of motion for the Goldstone node was just phi dot equals v. So there's no relaxation rate. So what we'll do is give a relaxation rate. Yeah, which I realized I forgot to write. So here essentially I've turned on some omega. This omega appears like phi dot plus omega psi. So psi dot plus omega psi equals v. So if you just solve psi dot plus omega psi equals 0, this gives you exponential decay. This is why I'm calling this a phase relaxation rate. When this is small, then the charge density wave is just weakly perturbed by these moving topological defects, but when it gets big, at some point it completely destroys the charge density wave, and I go back to a metal. You can see this from the formula from the new formula for the conductivity. Now you see that omega appears here and there. Take omega to be large in your head, like take the omega to infinity limit. Then you see that you can neglect these terms. You can neglect the frequency dependence. The omegas upstairs and downstairs simplify out, and you would just get back the conductivity, the judo-like conductivity for a weakly coupled metal. If you set omega to 0, then you go back to this pin charge density wave state that I was showing you in the 2 slides ago. Now the DC conductivity, it's no longer, what did I do? I neglected, so when I wrote the DC conductivity here, for reasons that will become clear in the next slide, I've neglected this guy. The reason why I neglected it is that now this whole part contributes to the DC conductivity. I can rewrite it in this way. Except that now the rate that appears there, it's a mixture of the momentum relaxation rate and of things that are related to the charge density wave. So even when momentum relaxation is weak, this would still be non-zero because of this omega. So omega is important. It has a big effect on transport. And now I can plot what happens to the real part of this guy. And what I see is the following. Instead of having just a simple finite frequency peak, as was the case for the pin charge density wave, once I turn on this phase fluctuation rate, whether I get a peak at omega equals 0 or a peak at non-zero frequency is controlled by this inequality. I need pinning to be strong enough. This is what this inequality is telling me. In order for the peak to move off axis, pinning the charge density wave needs to get sufficiently pinned. If pinning is too weak compared to, say, this phase relaxation, then the AC conductivity has a peak at omega equals 0. The peak cannot move off axis. So now you see that it starts to look a lot like what we saw at the very beginning of the talk for bad metals. That there's this interpolation between peaks at 0 frequency and peaks at non-zero frequency.
Is this an empirical formula that you wrote there?
This is a formula that you derive from these hydrodynamic equations.
Okay. So it can be precisely derived.
Yeah. So from hydrodynamics, it can be precisely derived, except that, as usual, hydrodynamics does not tell me what this is, what that is, or that. So in particular, this picture is just really a picture, because to really connect that to bad metals, I would need to give you some microscopic derivation of how these guys depend on temperature, which I cannot. So now I can play a game. Let me neglect momentum relaxation. Take the DC conductivity formula from the previous slide, so I can rewrite it in this way. And now it turns out that if you look at the frequency-dependent formula. So omega naught still controls the location of the peak. Capital omega controls the width and height. So I can now just plug in what we read off from the data. You remember that from the data we saw that in this strange metallic regime, both the peak, location, and width were controlled by the same Planckian timescale. So this means that I can just plug that in, plug this formula in. And if I do this, I would recover exactly this linearity resistivity. Don't take this more seriously than it is. This is just a game that we can play with this formula. And what this game teaches us is that if you have these fluctuating charge density wave states, you have a natural way of relating the timescale that controls the DC resistivity to the timescale that controls the dynamics of the frequency-dependent conductivity. So the fact that these peaks are located at order temperature. This is what this toy calculation shows. It doesn't explain why you should plug that in the first place. It just gives you a mechanism by which you relate these two sets of quantities, which I think is nice. But now you should raise a few objections. First, you see that I've been talking about typical frequency scales that are of order temperature, like this omega naught. All of these were set by temperature. But in the lectures, I told you that in order to do hydrodynamics, you need to be able to write an expansion in small gradients. And small gradients meant essentially that the frequency scales had to be much less than temperature. So you shouldn't really take this hydrodynamic formula at face value. At best, we're at the edge of validity of hydrodynamics. So they're suggestive, but clearly you shouldn't stop there. This is not, this is some toy calculation that cannot be the serious calculation. The serious calculation, of course, would be to figure out what's the microscopic model that describes strange metals and then compute transport in that and match to the phenomenology, but of course no one can do that, so okay. I emphasize the role played by this Planckian timescale. This suggests that quantum criticality is important. So we should do a computation in some quantum critical theory. So the work in progress and now I'll talk a little bit about these last two papers on the reference page, and I won't take you all the way because we haven't gotten there yet, but I'll tell you where we are, is to use gauge gravity duality to compute essentially in critical states what are the long wavelength dynamics of transport and see what we get. So in particular, this will allow us to compute all of these parameters, the phase relaxation rate, the momentum relaxation rate, the pinning parameter, etc., etc. So let's do that. So in order to do this, we need some time model to capture the long wavelength dynamics of the gallstones. There are serious people that are doing serious calculations where they're not using a time model, they just take some black hole in ADS, they look at spontaneous symmetry breaking so that like everything becomes spatially periodic. This is usually very hard, you need to do it numerically. I'm not a numerical guy, so I like to try to find analytical models that will avoid numerics, or at least avoid complicated numerics.
What kind of computation? So like RDO black hole or something?
What?
RDO black hole or something?
What?
Like gravity duality. So what kind of gravity duality is that?
For instance, you take Einstein Maxwell theory with a transaminase term, and then you find that the transaminase term drives an instability at low temperatures towards a spatially modulated phase. So the picture, so this would be the serious calculation to do. Then you would take the long wavelength dynamics of this spatially modulated black hole, compute the conductivity, see what it looks like. Here, what I claim that this time model captures is directly focusing on these long wavelength dynamics. And I'll give you some supporting evidence that this is correct. You can see it looks a lot like this holographic time model I was talking about in the lectures, except that I've added some real scalar phi that will just be radially dependent, that will drive the RG flow to interesting places. But you have the same size, these massless scalars that I take to be linear in the spatial coordinates. But if you remember, this was a time model that I told you in the last lecture that this captured explicit symmetry breaking. But now I'm telling you that I want to use this for spontaneous symmetry breaking. So how does it do this? Well, to get spontaneous symmetry breaking, you have to play a little bit with UV boundary conditions, essentially. So let me just, for now, just as an example, pick this coupling Y between the spatially dependent scalars and phi to just be phi squared. Then I can just rewrite this whole part as a pair of complex scalars. So phi will be the modulus of the complex scalar, and the psi's will be the phases of the two complex scalars. So you can, essentially what I'm trying to say is that you can always think of this model as long as the UV behavior of this coupling goes like phi squared. So it means that it needs to vanish sufficiently fast. Then you can always think of this model as some CFT deformed by a pair of complex operators. Now, that's exactly what people do in mean field treatments of charge density waves. This you can understand from remembering this formula that I wrote here. Obviously, this I could rewrite as a complex scalar with an amplitude rho naught and some phase that has a background value that's just linear in the spatial coordinates. So essentially, I'm doing the exact same thing in this holographic model. Okay, and now it's obvious that if I set the source of these complex scalar deformations to 0, then I have spontaneous symmetry breaking. I don't have explicit symmetry breaking. So that's what we'll do. We'll compute the response for a background where this phi of r only has a valve and no source. And this will capture spontaneous symmetry breaking, and we'll see that. So you remember, I computed the conductivities in this toy model in the lectures where the breaking was explicit, and we saw that the conductivities were non-zero, they were finite. They were given by this momentum relaxation rate. So here I'll compute the conductivity again, but what we'll see is that, well, I will tell you, I'll show you because we're not going to have the time, but that the conductivities with these boundary conditions are now no longer finite. They have some pole at omega equals 0, simply because translations are broken spontaneously.
So F is a Maxwell field?
Yes, F is charge, yes. So before we talk a little bit about the conductivity, what we can do is compute the equilibrium stress tensor. You just start from the equilibrium black hole, compute the dual stress tensor. What you find is that it exactly, at least the spatial part of the stress energy tensor, exactly matches what you expect from a Goldstone, from a charge density wave state. So this is the stress tensor that you would derive from hydrodynamics, and you see that it differs a little bit from what I was showing you when we were talking about hydrodynamics in the first lecture. In particular, so when we were doing fluid hydrodynamics, in the spatial part, you would only have the pressure times the metric. Now, the fact that you have these Goldstones means that you have other terms that are allowed in the equilibrium stress tensor that are derivatives of the Goldstone. And remember that the equilibrium value of the Goldstones are just like essentially x. Now, these new derivative terms, they come with coefficients that are called the shear and the bulk modulus. Essentially, they parameterize the elastic response of your state, because these Goldstones, they're phonons, so you can think of them as they're like little springs. So you can compute what the bulk modulus is just from the equilibrium black hole. So here's a specific formula in terms of these functions in the black hole metric and this coupling y between the phi and the psi's. And yeah, this is essentially what these moduli do. Like bulk modulus is uniform compression, and shear modulus is strain like this. So this is nice because it means that just from thinking about this black hole model, we already get the right form for the equilibrium stress tensor. Then what we did is we computed the conductivity. What do we expect for the conductivity? Well, remember that for a pin charge density wave, this is what it looks like. Now, if I set omega naught to 0 and gamma to 0, then I would just get some omega equals 0 pole, right now I'm not, I haven't broken translations explicitly, so this is what I expect to get. And it did, I mean, okay, I'm not showing this for lack of time, but this is exactly what we saw by solving numerically using the background black hole, where you perturb around it, you get the conductivity, you find that there's this O at omega equals 0. So indeed, the breaking is spontaneous. But one thing we did is we were interested in computing this sigma naught coefficient, because as I told you, this is what captures the DC conductivity when the translation symmetry breaking is weak. And that I can compute in the clean theory. So it means I can compute that in this toy model that I was showing you, where the breaking was just spontaneous. So we did that, and the way we did this is exactly the way I showed you during the second lecture. So you turn on some sources linear in time, except that now we turned on both an electric field and a temperature gradient. And then what we did is we fixed a linear combination of these two sources in such a way that we don't source momentum. And then by the same manipulations as I showed you, you can extract this incoherent coefficient. And at low temperatures, what you can show is that it looks like this. So there's some prefactor, which is just thermodynamic data. This is the bulk modulus, this is the chemical potential, the charge density. And then there's another part which is solely given in terms of data on the horizon. So this Z, this is the coupling between the Maxwell field and the scalar phi. This is evaluated at the black hole horizon. Here you have the charge density squared. So again, that's the electric flux emitted by the black hole horizon. This K is the parameter that breaks translation symmetry. Y is the coupling between phi and size, and S is the entropy density. So there's this structure. There's a thermodynamic data that cannot be solely determined at the horizon. Remember that K, to make this very precise, I told you that the bulk modulus, this is given by this integral. This is an integral over all of spacetime. So I need to know the full spacetime in order to compute that. But if I want to compute this, I just need to know what's going on near the horizon of the black hole. 5 minutes, is that right? Let's see. 6, 7. Maybe, let me skip this. If you want, I can tell you about it. But essentially what you do is that you can play games with scaling properties of the horizon, of the extremal horizon. The simplest case is that, and this is what I'll focus on, you can just find that the horizon is ADS2 cos R2. That is within this toy model that I was telling you about, I can pick the couplings in such a way that the black hole flows to ADS2 cos R2 in the IR. So exactly like Weiss-Nordström, except that now I'm breaking translation spontaneously. So then I can plug the form of the solution in this conductivity that I just computed. And then I would find that the conductivity goes to a constant at 0 temperature. So there would be some higher temperature dependence, but at 0 temperature, the conductivity goes to a constant. Now I can play wishful games again, and I can compare that to, so this is some high TC superconductor at underdoped, underdoping, and the LSCO. And you see that this is an interesting compound because at exactly the doping at which this was measured, the superconductivity vanishes, so you can go all the way down to 0 temperature. Whereas you see that for this compound that's a little bit different, at some point you hit the critical temperature, the resistivity plummets to 0. In this guy, there's a specific point in doping where you have superconductivity on the left, superconductivity on the right, but right in the middle, you can go to 0 temperature all the way down. That's because this is precisely the region where they've detected that this charge density wave order is strongest. And when charge density wave order sets in, this is this little kink here. And then the conductivity rises up and goes to a constant. So that's kind of reminiscent of what's going on here. I'm not saying that these are described by ADS2 cos R2 IRs, but certainly that's one of the things that you can keep in mind. There's another case that's interesting, which is, so forget about disease and thetas, you can ask me later, but which is when the IR geometry is not exactly ADS2 cos R2, but it's conformal to it. So there's a factor of ADS2 cos R2, and then there's some overall power of the radial coordinates, so that the geometry is just conformal to that. This this leads to a conductivity that goes like 1 over temperature. So this means that the resistivity in turn will go like linear in temperature. So this looks a little bit like what you would have at optimal doping. This color coding is telling you how the resistivity is scaling. So in the middle region, you see that it's this linear in T resistivity I was telling you about. So I guess the message I want to get across here is that using these types of formulae, you can get many different scalings. So you can sort of classify these scaling behaviors and understand exactly what you need to do in order to get this or that scaling. So now I want to conclude by going back to this picture about the frequency-dependent conductivity. So right now, I only told you about the exactly spontaneous case. But what we're doing these days is we're turning on a small source. So if we turn on a small source for the scalar field for this phi, now we're breaking translations explicitly a little bit. If the source is small, this is pseudo-spontaneous breaking. If the source is large, then it will be completely explicit, but if it's small, it's pseudo-spontaneous. Essentially, we want to try to get something that looks like this. And this is what we see. This is at high temperature, then we're lowering the temperature, and you see that this peak that's off-axis moves back here and becomes a peak centered at omega equals 0. So it's very reminiscent of what's going on here. But it's also very mysterious, because here I was trying to tie this behavior to the fact that there was phase relaxation by moving topological defects, moving dislocations. Well, as you could see from these black ansatz that I had, this was completely homogeneous. The only spatial dependence was in this size, it's linear in x, but then everything else, it's just radially dependent. So there's no way that there are topological defects here. We just don't have vortices, and I'm sure of that. So yet there's something in the system that's playing this role, the same role somehow. And I have ideas that I'm happy to talk about, but not to publicly present yet, because it's still a little bit rough, but we think we understand maybe why that's the case. For now, we've just constructed a geometry that goes like ADS2 in the IR, so the position and width of these peaks at low temperatures, they become constants. But certainly, we're hoping to construct other examples with this more general IR behavior, like conformal to ADS2, and see if we can get these things to move with temperature. So, yeah, that's it. Thank you.
Any questions?
Well, I have a question. Do you draw a phase diagram in which there's some superconducting phase and it goes up, then the strength and so on? This is what you describe.
Not really.
Not really.
I'm not trying to describe, so this was the phase diagram. Yeah, this is the phase diagram that you are referring to.
Yes.
So, yes, perhaps I could imagine constructing some toy model, some holographic toy model that has all of these phases. But, I mean, first, this is supposed to be a conventional metal, so this is supposed to be weakly coupled. So then why would I use ADS-CFT to describe any of that? This superconducting phase, it's more or less well understood in terms of D-wave superconductivity, etc. It's not completely obvious that this is well captured by anything that's right. Yes, the main problem with this guy is that this is a D-wave superconductor. So a D-wave superconductor has an order parameter which is spin 2. Most people that have worked on holographic superconductivity use S-wave. So they model that by a charge complex scalar that condenses. But if you want to do this with spin 2, then you're in trouble, because you need another spin 2 field that couples to gravity. And it's kind of hard to come up with healthy theories that do this with just a spin 2 field. People in massive gravity have been talking about this for ages. So, I mean, you can do this as a probe, but to have a back-reacted phase, then that's much harder to find a healthy gravity theory that can do this. So essentially what I'm more interested in is to try to, so these are regions where we know that things are strongly coupled. So certainly I think these are the regions that I'm thinking of. And I'm not necessarily exactly, I'm not trying to match any microscopic details. I want to understand qualitative trends. Like what kind of ingredients do you need in order to reproduce the phenomenology that you get? I don't really care about matching prefactors, for instance. Like if they measure that the resistivity is linear in T with 1.4 in front, I don't believe that ADS-CFT is the right tool to compute this 1.4. But maybe ADS-CFT is the right tool to understand why this linear in T resistivity is there across many different materials, not just ITC superconductors, but many different metals that have completely different atomic structure. So in the UV, these things look nothing like each other, and yet in the IR, they all behave the same. So that kind of questions, I think ADS-CFT can be useful.
Well, that's not my question. I suppose, roughly speaking, I'm trying to describe the strange metal phase.
Mm-hmm.
My question is, if you go to the boundaries of this strange metal phase, how do I describe this limit?
This is complicated. It's a complicated question because you see, I didn't draw this as a solid line, which means that people have not detected a sharp phase transition there. So there's some meaning to this line, and this whole region is actually called pseudo gap, where it means that they see that there's a gap that opens in the density of states here, but there's no condensation of an order parameter. So they don't know what this phase is. What they do see is that there are many competing orders in there. They can be charge density waves, they can be spin density waves. Now they're even detecting some nematicity. So nematicity is the spontaneous breaking of rotations without breaking translations. So, again, you can try coming up with some holographic model that would, capture all of that. But I sort of doubt that, it would become very complicated and very fine-tuned. The question I'm asking is more along the lines of, what are the general features of transport in a strongly coupled metallic or charge density wave phase? And how does this allow me to understand something about the transport phenomenology of these materials?
So you think in general there are several types of transportation methods in the one system, and then each of them competing, but in that phase, when you describe it, the most probable.
What I'm saying is that, things are messy. It's definitely been established that you have charge order there, that they can be pretty strong depending on materials. And so what I'm saying is, if we're in a case where we have a strong charge ordering that is probably dominating other forms of order that might have appeared, then this is how transport would look like. And does this match what we're seeing? And it's true that I've only shown you, for instance, in this plot where I was showing the width and position of the peak, the list of materials that I was showing is not complete. There are certain materials where you don't see this happening, where you don't see the peak moving off axis. But this could be due to many things. It could be due to the fact that there's, for some reason in that particular material, there's some other form of order that is stronger, or the pinning is not sufficiently important, or things like that. So that's why I'm saying things are messy. But at least from a theoretical standpoint, you can ask, what are the general features of transport given a certain pattern of symmetry breaking? And that's a well-defined question. Then how far you can push the comparison to experiments, this is a different topic.
Any questions? Okay, let's thank Blaise again. And we meet at